Dear viewers, this is video part 4 of the 7-part series on lymphocytes and immunity in the Medicine for Anyone in the YouTube channel. Specific attributes of the B lymphocyte system, humoral immunity and antibodies. Antibody formation by plasma cells. Before exposure to a specific antigen, the clones of B lymphocytes remain dormant in the lymphoid tissue. On entry of a foreign antigen, macrophages in lymphoid tissue phagocytose the antigen and then present it to adjacent B lymphocytes. In addition, the antigen is presented to T cells at the same time and activated T helper cells are formed. These helper cells also contribute to the extreme activation of the B lymphocyte. The B lymphocytes specific for the antigen immediately enlarge and take on the appearance of lymphoblasts. Some of the lymphoblasts further differentiate to form plasmablasts, which are precursors of plasma cells. In the plasmablasts, the cytoplasm expands and the rough endoplasmic reticulum proliferates vastly. The plasmablasts then begin to divide at a rate of about once every 10 hours for about 9 divisions, giving a total population of about 500 cells for each original plasmablast in 4 days. The mature plasma cell then produces gamma globulin antibodies at an extremely rapid rate, about 2000 molecules per second for each plasma cell. In turn, the antibodies are secreted into the lymph and carried to the circulating blood. This process continues for several days or weeks until finally exhaustion and death of the plasma cells occur. Dear listeners, by the way, this educational video is made possible by Prescribe-On, the makers of e-prescription software for digital prescriptions, available freely for doctors on the website www.prescribeon.com. Doctors who are interested in this e-prescription can freely avail of its vast collection of more than 100,000 e-prescriptions. Formation of memory cells enhances antibody response to subsequent antigen exposure. A few of the lymphoblasts formed by activation of a clone of B lymphocytes do not go on to form plasma cells, but instead form moderate numbers of new B lymphocytes similar to those of the original clone. In other words, the B cell population of the specifically activated clone becomes greatly enhanced and the new B lymphocytes are added to the original lymphocytes of the same clone. They also circulate throughout the body to populate all the lymphoid tissue. Immunologically, however, they remain dormant until activated once again by a new quantity of the same antigen. These lymphocytes are called memory cells. Subsequent exposure to the same antigen will cause a much more rapid and potent antibody response the second time around because there are many more memory cells than there were original B lymphocytes of the specific clone. This figure shows the time course of antibody response. First time exposure has a delayed response, which is weak with a short half-life. The second time response elicits far more potent response and lasts for a longer time. See the figure time course of antibody response shown just earlier. This shows the differences between the primary response for forming antibodies that occurs on first exposure to a specific antigen and the secondary response that occurs after second exposure to the same antigen. Note the 1 week delay in the appearance of the primary response, its weak potency, and its short life. The secondary response, by contrast, begins rapidly after exposure to the antigen, often within hours, is far more potent and forms antibodies for many months rather than for only a few weeks. The increased potency and duration of the secondary response explain why immunization is usually accompanied by injecting antigen in multiple doses with periods of several weeks or several months between injections. Generation of lifelong immunity by plasma cells. When naive, that is unexposed B lymphocytes encounter their associated antigens, become activated and undergo clonal expansion. They differentiate into short-lived or long-lived plasma cells that produce large amounts of antibodies. The short-lived plasma cells provide rapid protection but undergo apoptosis after a few days of intense antibody secretion. However, the long-lived plasma cells reside in tissues such as the bone marrow and gut-associated lymphoid tissue and can continue producing antibodies for many years, providing lifelong immunity against infectious diseases such as measles and smallpox. High titers of smallpox specific antibodies, for example, have been detected in the blood of subjects vaccinated in childhood 70 years previously. Also, older survivors of the 1918 H1N1 influenza virus pandemic were shown to possess highly functional virus neutralizing antibodies to this virulent virus 90 years after they were infected. Thus, plasma cells that produce virus neutralizing antibodies can be sustained for many decades after exposure, even into the 10th decade of life in humans. Humoral mediators of adaptive immunity. Immunoglobulins. Immunoglobulins are the products of differentiated B cells and mediate the humoral arm of the immune response. The primary function of antibodies are to bind specifically to antigen and bring about the inactivation of or removal of the offending toxin, microbe, parasite, or other foreign substances from the body. The structural basis of Ig, that is immunoglobulin molecule, function, and Ig gene organization has provided insight into the role of antibodies in normal protective immunity, pathologic immune-mediated damage by immune complexes, and autoantibody formation against host determinants. Immunoglobulins are composed of two heavy polypeptide chains as in the figure and two light polypeptide chains. The antigen binds at two different sites on the variable portion of the chain as shown in the upper part of the picture. See figure structure of typical immunoglobulin IgG. Antibodies are gamma globulins called immunoglobulins. They have molecular weights between 160 and 970,000. They constitute about 20% of all the plasma proteins. All the immunoglobulins are composed of combinations of light and heavy polypeptide chains. Most are a combination of two light and two heavy chains, as shown in structure of typical immunoglobulin G, IgG. However, some immunoglobulins have combinations of as many as 10 heavy and 10 light chains, which give rise to high molecular weight immunoglobulins. Yet, in all immunoglobulins, each heavy chain is paralleled by a light chain at one of its ends, thus forming a heavy light pair. There are at least 2 and as many as 10 such pairs in each immunoglobulin molecule. The figure structure of typical immunoglobulin shows a designated end of each light chain called the variable portion. The remainder of each chain is called the constant portion. The variable portion is different for each specific antibody, and it is this portion that attaches specifically to a particular type of antigen. The constant portion determines other properties of the antibody, establishing such factors as antibody diffusivity in the tissues, adherence to specific structures in the tissues, attachment to the complement complex, ease with which the antibodies pass through membranes, and other biological properties of the antibody. A combination of non-covalent and covalent bonds, that is disulfide bonds, holds the light and heavy chains together. Specificity of antibodies. Each antibody is specific for a particular antigen. This characteristic is the result of the unique structural organization of amino acids in the variable portion of the light and heavy chains. The amino acid organization has a different steric shape for each antigen specificity. So, when an antigen comes into contact with it, multiple prosthetic groups of the antigen fit as a mirror image with those of the antibody, thus allowing for rapid and tight bonding between the body antibody and antigen. When the antibody is highly specific, there are so many bonding sites that the antibody antigen coupling is exceedingly strong, held together by hydrophobic bonding, hydrogen bonding, ionic attractions, and van der Waals forces. Van der Waals forces are weak electrostatic forces that attract neutral molecules to one another. Note, especially in the figure structure of immunoglobulin, that there are two variable sites on the illustrated antibody for attachment of antigens, making this type of antibody bivalent. A small proportion of the antibodies, which consist of combinations of up to 10 light and 10 heavy chains, has as many as 10 binding sites. 5 general classes of antibodies. There are 5 general classes of antibodies, respectively named IgM, IgG, IgA, IgD, and IgE. Ig stands for immunoglobulin, and the other 5 letters designate the respective classes. Immunoglobulin G constitutes about 75% of the antibodies of the normal person. IgG antibodies are frequently the predominant antibody made after re-challenge of the host with antigen, that is secondary antibody response. Serum half-life 23 days, rate of synthesis 33 mg per kilogram per day, antibody valency bivalent. Immunoglobulin A constitutes about 7 to 15% of the antibodies of the normal person. IgA is the predominant class of immunoglobulin in secretions. IgA in secretions like tears, saliva, nasal secretions, gastrointestinal tract fluid, and human milk is in the form of secretory IgA. IgA fixes complement via the alternative complement pathway and has potent antiviral activity in humans by prevention of virus binding to respiratory and gastrointestinal epithelial cells. Serum half-life 6 days, rate of synthesis 65 mg per kilogram per day, antibody valency bivalent. Immunoglobulin M constitutes about 5 to 10% of the antibodies of the normal person. A large share of the antibodies formed during the primary response are of this type. IgM is an important component of immune complexes in autoimmune diseases. For example, IgM antibodies against IgG molecules, that is rheumatoid factors, are present in high titers in rheumatoid arthritis, other collagen diseases, and some infectious diseases such as subacute bacterial endocarditis. These antibodies have 10 binding sites that make them exceedingly effective in protecting the body against invaders, even though there are not many IgM antibodies. Serum half-life 5 days, rate of synthesis 7 mg per kilogram per day, antibody valency 10 or 12 valencies. Immunoglobulin D constitutes about 0.3% of the antibodies of the normal person. Serum half-life 3 days, rate of synthesis 0.4 mg per kilogram per day, antibody valency bivalent. Immunoglobulin E constitutes about 0.02% of the antibodies of the normal person, especially involved in allergies. IgE, which is present in serum in very low concentrations, is the major class of immunoglobulin involved in arming mast cells and basophils. It is involved in release of mediators of the immediate hypersensitivity, that is allergic response. Serum half-life 3 days, rate of synthesis 0.016 mg per kilogram per day, antibody valency bivalent. So, dear viewers, this is the end of part 4 of the 7-part series on lymphocytes and immunity in the Medicine for Anyone in the YouTube channel. Thank you for watching the video.